Yeah. That's what we use. All these people, you hate, like you're not to this. What? Yeah, like. What is that? What is that? What? Oh, tell the person. That's a even with some. I cannot.
Good afternoon. So I want to go over these type of ODEs to solve today. So far in the course, we have, or so far in this module, we have seen two methods, Euler's method and Runge-Kutta second order or RK2 method. There is one more method to see called RK4. RK2 involves evaluating the function twice. RK4 will involve evaluating the function 4 times. It's not super different from RK2 itself. So I'm planning to discuss that on Tuesday. From the perspective of the exam, I can tell you for almost guarantee that I'm not going to ask you a problem that is just a first order equation. Dy over dt is a function of y and t. This is not going to be on the test. What is going to be on the test is either a second order differential equation or a system of two coupled differential equations that you will have to solve using one of these methods. Okay, so we want to learn that today, how to apply these methods for solving a second order or higher order differential equation and solving a system of 2, 3 or more number of coupled ODEs. Okay, so that's what we are going to learn today. Any questions from this topic so far? Like so far, are we all on the same page about using Euler method and RK2 method to solve ODE? Are we all together? Did you start attempting the participation exercise or maybe uploaded it? I don't know. Did you attempt? Because that's the last remaining participation exercise to solve that problem. Dx over dt equal to minus xt with x of 0 equal to 1. To solve this problem using Euler, RK2 and RK4 and upload the Excel sheet, that's the last participation exercise. Okay. So if you haven't done that, please do. But today we are focusing on how to solve a second order equation and a system of two equations. Okay. Any thoughts? Anyone wants to say what we should do to apply what we know to a problem that we don't know yet? What can we do to reduce this second order equation to a first order equation? So you can write the second derivative as the derivative of the first derivative. You can do that, can't you? Right? The second derivative is the derivative with respect to time of the first derivative. Okay. So I'm going to make the substitute or define a new variable z, which I'm going to call is dy over dt. Substitute z equals dy over dt. As part of the initial conditions, we are told what is the position or what is y and y dash at time 0. What we are essentially saying is this implies z at time 0 is the value of the first derivative of y at time 0, which is 0 in this case. we have added an additional ODE dy over dt equal to z. Okay, dy over dt equal to z. Okay, with the initial condition or with the condition that y of 0 equal to 2, and this equation becomes dz over dt equal to minus y plus 2t, and z of 0 is 0. So you have two ODEs. I'm making a substitution for the first derivative. We have reduced the second order ODE to a bunch of two first order ODEs, which we know how to solve. Is that landing? We just reduced the second order ODE to a first order ODE, or two first order ODE. This problem, on the other hand, doesn't ask you to do such a substitution or anything. It just is stated as two variables or an ODE in terms of y and z, which depend on the right side, which depends on y and time in this case, and y and z in this case. So both problems are kind of the same template. Two ODEs, two first order ODEs, two first order ODEs. Okay, it's just asking you to do twice the work. That's it. When you solve these problems, we have to solve for y and z simultaneously. Can somebody tell me what simultaneously means? What does it mean in practice? Like what does, okay, simultaneously means same time. How will you implement it, or how will you incorporate it in your workflow? So let's say you have time axis. Okay, and in the y-axis, let's say we plot y of t, and also we'll plot z of t. That is two quantities that we are plotting after you solve for them. Okay, at the start, at time 0, you are given initial conditions for both y of 0 and z of 0. Y of 0, z of 0. So they'll have some values. Okay, we'll call this y of 0, and this is z of 0. Those are the initial conditions. Are we okay? Everybody who's writing is caught up? Yes. Okay. So here's what simultaneously means. Okay. Pay attention. Look up. So from time 0, if my delta t happens to be 0.1 or whatever, I want to solve for the next time point for y and next time point for z. Y of 0.1 and z of 0.1. Y, the solution for y will generally depend on what the previous value of y and x, both of them. It will rarely depend on only y, like in this example here, it depends only on y and t, but generally it will depend on y and z. In fact, z here depends on y and z. So if you want to evaluate z, you have to know both the previous values of y and z. And if you want to evaluate the next value of z and the next value of y, this depends on both of these. This depends on both of these. So before you advance to the next time step, you should have solved for both the quantities involved and not only one of them. That's what simultaneously means. That makes sense? You have to, at every time step, you have to solve for all the variables in your system. There could be 2, 3, 4, 20 variables, whatever the number of variables are. You should update all of them before you move to the next step. That's what simultaneously means. Okay. So this is a very important point to remember, because like in this problem, the solution to y depends on z. The solution to z depends on y. So when you advance to the next step, you should know the latest value of both y and z in order to progress. In this problem, z depends on y and z. Y depends only on y and time. Okay. So over here, in this one, y depends on z. Sorry, y depends on z, and z also depends on y. So the coupling is two-way coupling. This problem just happens to be a case where z depends on y, but y doesn't depend on z. This is one-way coupling. It's kind of a special case. This example is just a quirky one, a rare one, or an uncommon one. You should be prepared to assume that most problems will have two-way coupling. It's better to solve for both the variables at each step as you progress. Okay. Are we ready to solve this problem? We have seen all the theory or concepts. Now we want to start putting down numbers. Any questions before we do that? Okay. We'll do this problem. Okay. Can I erase this? Yes. And we are going to use Euler method because that's the simplest for learning. We don't want to super complicate this. Okay. So I'm going to rewrite this up here. dy over dt in general can be a function of f of y, z, and t. Sorry, in this case, dy by dt is just z, and dz over dt is minus y plus 2t. If you forget z, or you forget, this is nothing but d squared y over dt squared. Okay. With the initial condition, y of 0 equal to 2 and z of 0 equal to 0. Always set up a table. Table to keep it organized, and recall Euler's method. In the exam, this will be provided to you. You don't have to remember, but you should know how to use it. So if you have any equation, dx over dt is a function of x and time. Xi plus 1 is xi plus delta t times f of xi comma ti. This is what Euler's method is. Will be given in such a general notation. Okay, you have to apply it for your problem. So we'll start with iteration number, time ti, or I'll say I ti, xi, sorry, not x, yi, zi, okay. Since we have to evaluate the function only once, I think this should be enough, and we can track error in y and error in z. So you can call the initial condition, say, 0th iteration, This is initial condition, time 0. Yi is 2, z of 0 is 0, and error is not yet defined. Yes.
The DC over DT equation, why are we using a 2T instead of 1.5?
Oh, human error. Copying error. Okay. Next iteration, I want to use a time step of delta t is 0.1 as suggested, so 0.1. And all the values that I calculate in the second row will depend only on the values on the first row, okay? And it won't depend on this time yet. So y1 is y0 plus delta t times, I should look at this equation, which is times zi. So z0, that is y0 being 2 plus delta t being 0.1 times z0 being 0, which gives me 2. So y1 is also 2. Z1 is z0 plus delta t times, I should look at this function, which is minus y0 plus half t0. So this is z0 is 0 plus 0.1 times minus y0. Y0 is 2 plus half times t0 is 0. So I get minus 0.2. So z updates to minus 0.2. I'll give a minute. Please make sure you understood what I did, especially this step here. Why this is z naught? Why this is minus y naught plus half t naught? This is the right hand side of dy by dt equal to f of y comma z comma t. This is z. This is the right hand side. And then this is dz over dt is, let's say, g of y comma z comma t. This is minus y plus half t. If you understand this step, you are basically set for the rest of it. Are you okay, Sean? I'm just, no, I'm saying this step makes sense to you?
Yeah.
Okay. We are about at the end of the term, thinking if there are people whose names I don't know yet. Michael, Rashid, Calvin, right? Calvin, Carson, David, Patrick, Ansar, Sandy. Sorry, what's his name?
Chase.
Chase. Yeah. Chase joined. Yeah. The name?
Thomas.
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 Last name?
Murphy.
Murphy. Madison.
Elias.
Alex. Thomas. Sean. Brian. Daniel. Wait. Jonathan. Brian. Emilian. What's your name?
I got that call with the on the list. It's Nicholas.
Nicholas. Okay. Edith. Edith. What's your name?
Simon. Simon.
Simon.
Caleb.
Caleb. I know you. Brian. No, sorry. Bradley. Zane. Elijah. Okay. Okay. Okay, are we good? Can we do the next iteration, please? 2, the time is 0.2, and we have to update the values of y and z. That's why it's crucial to update both of them. So now I'm going to write y2 is y1 plus delta t times delta t times z1, which is y1 is 2 plus 0.1 times z1 is minus 0.2. So I get 2 minus 0.02 or 1.9 each. $1.98. And then Z2 is Z1 plus delta T times minus Y1 plus half T1, Z1 being minus 0.2 plus delta T is 0.1 times minus 2 plus half, T1 is 0.1. So this is minus 0.2 plus 0.1 times, this is minus 1.95. So this is minus 0.2 minus 0.195. So that's minus 3.395. Can you tell me if you are also getting these numbers? Are you getting these numbers? Yes, no?
Yeah.
Yes, okay. So now we have completed 2 iterations. Now is the time where you can check what is the error, meaning at what, I'm sorry. Okay, that would make sense only if we had an analytic solution to this problem, which we can get. Okay, this is not an impossible problem to solve analytically. That slipped my mind, so let's leave that. Let's do one more iteration and go to the other problem. 0.3. Please do that and let me know. Do we have some values for the third iteration? Yes. Can you tell me?
Y, it's 1.86. Z, negative 0.85, I mean, 0.83, 0.583, I'm sorry.
Okay. So you can see the method itself is not super complicated. Yes.
I got 0.5 or negative 0.583.
Why I got 1.9 for 5.
Okay, 1.94. Anybody else getting either of those?
I got the second one.
1.94. So I'm going to show this in Excel, so we'll quickly know. 1.94. So the method itself is not super complicated. The idea itself is not super complicated. The choice of numerical method, whether it's Euler or RK2 or RK4, between those methods, what's the difference? What did we learn last time? Which method is better? So if you want to use large time steps, typically the methods that evaluate the slope multiple times will get you better accuracy. So in terms of accuracy, for the same time step, RK4 will beat RK2 will beat Euler. This is an advantage for the higher order methods at low time step. That is, you can use a very coarse or a very high time step. The higher order method will get you good accuracy. But if you use a very fine time step, the returns get diminished. So if you want to do like a time step of 10 power minus 4, all the methods will kind of get you the same error, because this will get you maybe a little bit better, but you have to work a lot more for that. Okay, so that's why it's better to work with larger time step, as large as possible, and an algorithm that is as accurate as you can possibly construct or pick. Okay. The reason I started this problem with Euler is, if I make you do this with RK2 or RK4, you have to do more calculations. It just muddles up the message. Okay, so that's why we did this here. So I'm kind of halfway done setting up the Excel sheet to show you this. Why don't we get started on this problem? Same idea, nothing changes. Once you set up the substitution here, these two problems proceed identically. So why don't you construct a table like this for the second problem, and we'll discuss in like 5 to 10 minutes, depending on when you get done. So solve this problem, construct the same table. I'll be ready with my Excel solution for that. And last 20 minutes of today's class, Dr. Marchetta will be here to make a few announcements. So we'll wrap up at 3:45 and I get to go home earlier. You can stay on until 4:05. Okay. Yes? What? I mean, what? Dr. Marchetta? Maybe if I tell that, some of you will leave, and I don't want to be the reason for that.
I also.
That depends on whether that information is relevant to you or not, which I don't know what he's going to talk about. So I thought if Dr. Marchetta is coming, that will retain audience. I don't know why there is people trying to flee. Every day is one of those days. See the class, only half of the class is here. I should stop posting YouTube videos, but then I get all guilty and like, fine. So just because some kids won't show up, I don't want to punish the others. Yeah.
The crazy, the formula is the DC over DC, right?
Yes, you should take this and apply this step here. Like this see this Euler method I gave in terms of x like a generic thing. You have to apply it for this y variable and for the z variable. The z
No, for Y, I initially got 1.86.
uh, for here
No,
or
for
here
the third iteration.
1.94.
Yeah, I got 1.86.
You got 1.86. I don't think that's correct. My Excel also tells it is 1.9405.
I didn't get close.
So what I would like, this is very common. Like when you are sitting down to practice for the or prepare, you got to have a done solution with Excel, put that aside and then do the problem with hand, or do it first and then check your answer. I don't know, somehow it has come into the psyche that making mistakes means you don't understand something. You should view making mistakes as the way to understand something. So now you have a 1.86. You know the answer is 1.94. Now you go looking where you missed it. That's where you figure out where you missed it and what you missed, and then you fix that in your understanding. Next time you won't make that mistake. So this is advice for everyone. After, when you are taking the book and finding examples to practice, always keep Excel, solve it first in Excel, make sure that it's implemented correctly, then cross check your work. Sometimes you might make mistakes in your hand calculation, sometimes you might make mistake in your Excel calculation. Eventually they both should kind of get to the same point. That's one way to check it. The other way to check it is to take a problem for which there is a known analytic solution and use that to check your work. Okay, so it's not just that you will always be given some problem to solve and somebody is going to score you. At some point, you have to invent your own problem and your own validation method to check whether you're doing it right. Do we have numbers for the other problem? Okay, let's refrain from discussions or just fun talk. I know this class is not meant for fun. I take it very seriously. Okay, silence please. Okay, so this is problem 1. This is problem 2. Those who are working through problem 2, can you look at this and see if you are getting these numbers? Yes? Okay, good.
So D3.
D3? Okay. I'll give you guys like 5 minutes. Please wrap up this because I want to discuss something that could likely be an exam question, in the sense something that is good enough to be an exam question. So please, let's do this quickly.
D11.
D11, you got it.
You go to the cell to the left.
This one, C11.
Can you go back to the?
Sure, sure.
Thank you.
I can do this all day for you.
From the.
So this is what you have to produce in the exam. That is, if your problem is presented like this, you'll be asked to do maybe 3 or 4 iterations. If it is using a method like Euler, I might ask you 4 iterations. If it's a method like, let's say RK2, I might ask you fewer iterations, like 2 or 3. If it's RK4, no more than 2 iterations, because that's already 8 calculations that you have to do. Okay. So be prepared to do any of these 3 methods. Depending on the complexity of the method, I will adjust the number of iterations to keep the effort kind of the same. Okay. Are we good with this? Can we talk about, yes,
C5.
C5?
Thank you.
Yeah. And what I might also do is, let's say there are 10 values to be calculated here. I might give you 2 or 3 and ask you to compute the remaining 7 so that you get some kind of sanity check to do during the test. Because let's say this number 1.94 is given to you, and at this step you are not getting 1.94, which means by extension the other number can't be trusted either. So I'll try to make it kind of simpler for you to have a sanity check in between, and at every step you should be able to get both the numbers. So that is, if I had given 9.19, 1.94, you should get that as well as the other one. Okay. Or sometimes I might give you the value for the next 2 values in the 4th iteration and ask you to calculate the 5th iteration. Because I know to get the 5th iteration, you have to get the 4th iteration. But if that doesn't agree, that means you are not good, you are not on the right track there. So we'll try to help you out there. C11 again, yes. Good. Can we move on? Yes, no? Yes. Can we move on to the next problem, next example? We still haven't learned RK4. I'm saving that for Tuesday. Okay. And next Thursday, I will go over the mock exam and discuss the solution. Okay. I want to bring up this example. Problem number 25.25, page 754, if you have the book in front of you. Problem 25.25. It's also a fluid mechanics problem. So those who are in the fluids class, this could also show up in your file. Use the following differential equations to compute the velocity and position of a soccer ball that is kicked straight up in the air with an initial velocity of 40 meters per second. Dy over dt is v, the speed, and dv over dt is minus g minus cd over m multiplied by the velocity with the sign and the speed, which is just the magnitude. Okay, where y is the upward distance, v is the upward velocity. It clearly says v is upward, meaning upward has to be positive, which will make gravity negative. So since they have a negative sign next to gravity, it's implicitly said upward is positive, y is measured upward positive, and g is measured, or g is expressed as a negative number. Nobody is going to sit and explain this to you in the exam, of course, but you have to pick up these sign conventions from the problem. G is gravitational constant, CD is drag coefficient, M is mass. Note that the drag coefficient is related to more fundamental parameters by CD equals half rho A CD and so on. And using these numbers, you can calculate the lowercase CD. Of course, for our purposes, what I will do is I'll try to calculate CD over M and just give you a number. So it's like alpha times V magnitude. And alpha is given to you as some number. Okay. So what we want to calculate here is compute the velocity and position of the soccer ball. Position will obviously vary from what range? If the ground represents y0, okay, the ball is kicked from the ground at 40 meters per second. So at time 0, where is the ball? Ground, which is 0. Y at time 0 is 0. What is the velocity at time 0? Plus 40 or minus 40? Plus 40, because it's kicked up. Okay. So for both the ODEs, you have initial conditions. Y of 0 is 0. V of 0 is plus 40. And you have to solve for y and v as functions of time. That's what speed and velocity mean, or trajectory mean. You have to solve it for multiple time steps. Makes sense? The problem makes sense? So you're at the ground, you kick it up, the ball will rise up, which means y will increase, y has to reach a maximum, and then y has to start decreasing again. Velocity is maximum at the bottom, velocity will decrease as you go up, reach 0, and then accelerate again downwards. You have to see this trend in your calculation. If you don't see this trend, something goofy happens, you have to immediately understand you're doing some mistake. That's the purpose of having intuition, to check your work. Okay. Shall we do this problem? Do you want to write down this equation and the fact that it's 40 meters per second? CD over M, we'll just take a simple number, like for our purpose, we'll call it like 10. We'll call CD over M is 10. Okay. And we'll proceed. I have 20 minutes here, so can you please rush up? You are worried about sitting through 20 minutes, maybe that may not be useful. I'm losing 20 minutes. I mean, with this course, it's always a fight against time. We'll again use Euler method. And maybe later you should try also with RK2 or RK4 because that's more work. Okay, so I'm going to rewrite the problem so that you can just follow what I'm doing. Okay, so if I just implement the method to solve for the trajectory of the ball from the beginning where it was thrown up, it rises up. As you can see, y increases, but as it goes up, drag and gravity will basically reduce the velocity. And if I go through this, at some point, the velocity has to, the distance has to peak, and then the velocity has to go to 0. So if you see here around 21 seconds, the distance reaches its peak, and thereon the distance decreases and velocity starts inverting and starts falling. So here is the chart where this curve is for the distance or the height. It increases, reach a peak, and then falls back. The velocity the velocity you should read from the secondary axis here, starts at 40 and then decreases. I don't know why I'm plotting only up to 80, I'll check that. But essentially the velocity decreases and then continues to increase. Okay, confused here. Oh, sorry. So yeah, this is position, and this is the velocity. Okay. So this is what we'll get if we solve the problem using Excel. Of course, in the exam, you'll be asked no more than 3 or 4 iterations, depending on the method. Okay. All right. So I'll stop here. Thank you very much, Dr. Marchetta. All yours.